So this morning, my name is Alexei. I work for a company called Datadog, and this morning I'm going to talk to you about what we internally call the data mullet. We'll see what it means. And that's really our journey from, especially in the past couple of years, doing a lot of SQL, moving to no-sql and then to a mix of SQL and no-sql. So in this talk, I want to spend some time talking about what's called a dirty architecture, so dirty as in data-intensive real-time, and that we put together for a new application. That's datadog.com. And we had a limited budget to do that. And because we had the limited budget, no money to really buy servers, we ended up running on a public cloud. In this talk, I really want to focus on data stores. So I'm not going to talk about web frameworks or languages, but much more about picking what we figured out would be the right data store for the right problem. I want to give you some context first because I'm going to talk about choices we made. I think it's important that you know what the problem space is, at least at a macro level. So this picture should look fairly familiar. This is where you and I live every single day. So you have, whether you're a developer, operations, or DevOps, so we are in the middle. We're surrounded by typically things that we need to get our job done. So servers, tons of tools, applications, and so on. Now, that's a static picture. In reality, this is what we face is there's a lot, with all these tools, all these servers, all these apps, there's a lot of that's constantly happening. And so we have to pay close attention to everything, or as much as we can. But all these signals that you see, metrics, updates, alerts, and so on, they come from different management tools. And so it's really hard to get the data into one place and figure out what's happening. And with that hard data, the only thing that you can exchange, you can share between people is oftentimes when you have problems is like tension, grief, finger pointing, and so on. So when things get out of hand, this is sort of what we end up having, sort of a nice collaboration. Now, concurrently, so I've very briefly mentioned the problem space that Datadog is operating in, what it is that we do. And that's important so that, you can understand the choices we made. So the first thing that we figured we'd do is we'd aggregate all these crazy signals into one place. And then, tag and categorize. And the reason why we would want to do that is so that you could do essentially two things. The first one is you could watch, and that's the happy guy on the top, watch in real time, using sort of dashboards and news feeds, what's happening across your entire infrastructure, across all your application, across all your online services, that you happen to be using, your monitoring system, and so on. The other class of use cases that you could do is actually look at the data. So now you have all the data in one place. Not necessarily focus on looking at real time, but rather sort of explore, deep dive, look for patterns. And then the third use case that we want to allow is to actually exchange insights about the data. So sharing, you see a pretty graph, you want to share it right there without having to drop to a third medium, like taking screenshots and copying to email or to a chat room and so on. And I should say that sharing is really, really important to us. So, data coming in from your systems, that's a constant telemetry, and then it's sort of splits into two use cases. One is, real time, you want to watch what's happening all the time, and, sometimes you drop of that mode and you see some interesting piece of data, you want to drill down, you want to look at what's happened in the past, you want to look for correlation, you want to see, if some kind of event happened, at the time you had some variations in some metrics. So what that led us to do is to have as simple as we could data taxonomy. So when you think about all these signals that we're talking about that's surrounding us, we decided to basically make or categorize anything that comes to Datadog as one or two things, either events or metrics. Now, events are, so it could be conversations, alerts from your monitoring system, a particular deploy that happened, a source code commit, and so on. So these are discrete events that carry meaning. So something where you can sort of understand them out of context. And that's very different from a metric, for instance, number of unique visitors, load, transaction duration, you name it, where one individual data point doesn't really make sense. What really makes sense is the whole time series. So in our problem space, we're trying to make sense of all that's happening around us. What we end up doing is taking everything, all the input signal, turning them into either events or metrics. And we wanted to stay at a fairly high level because it makes it a lot more, it's a lot easier to understand. It's a lot easier to grasp when you're using the app. One word about what is our unit of scale. So our unit of scale, and as opposed to talking about how much data we're processing, I'm going to talk about what are the little nuggets that we ingest. So typical unit of scale for a time series, they come from, by and large, servers. One server would typically run a couple of applications. So we'll track, say, 100 metrics, and we'll emit a data point every 15 seconds. So that's 24,000 points per hour. And at roughly 3 bytes per point, so you figure you need a timestamp. Then you need the value to represent your metric. That's give or take 3 bytes. So that's 100K an hour, or less, a little bit under 1 gig per year. So that's for metrics. For events, we don't of course get events every 15 seconds. We get events as soon as they arrive, at the resolution down to a second. And an event, I said it's a meaningful, discrete thing that happens. It has a little payload and a little bit of metadata, but it's not something that's that's on the same order of magnitude in sort of storage as a time series. Okay, so now I've described the problem space generally. Concretely, you kind of have a sense of the use cases that we allow you to, we support, I should say. And I just want to spend just a few moments on these 3 terms before sort of really digging in. So because I'll make references to them. So we have basically, you can categorize the data stores in 3 big buckets. The ACID one, which is your traditional relational database. The base one, which is a sort of basically available soft state, eventually consistent data store. Things like you can think, DNS I think is a pretty good example of it'll never quite be. It might never completely be consistent all across the board, but eventually, you'll get there. And the last one, which I think is more interesting, and that's really what I want to focus on this talk, is DIRT, which Brian, I don't know if it's in the room, coined, I believe, last year. So it's data intensive in real time. So let's dig some dirt, as it were. So I want to focus first on the real-time aspect and how conceiving an application that operates in real time, what kind of consequences does it have? The first one is one of latency. So if you look at our application where it's serving people who are bombarded with signals from their monitoring system, their build, their deploys, their services, their apps. So we built Datadog specifically so that the data could be aggregated and tagged and categorized, but ultimately consumed by people. So in terms of latency and how fast we have to respond, that gives us some interesting bounds, upper and lower bounds. So on the upper bound, we figured, from the moment something happens to the moment you can see it, we should be in the ballpark of like 15 seconds or so. The reason is basically that you want to, when you're looking at data, it's good to have stuff that moves. You don't want to, just have something that refreshes once every half hour because it's not as entertaining. B, it doesn't really enforce that you're looking, you're looking at live data, obviously. Now, on the lower bound, like 5 seconds, so it wouldn't make sense for us to try to react in 2 milliseconds. And the reason for that is once we present you with the data, it'll take you a couple of minutes to reach some kind of action or decision, more often than not. So because you need to digest what it is, it's this server went down while that metric shot up, and let me see, did we have a release in the past 5 minutes, and so on. So that really helps us not being completely driven to, we need to react in less than 3 milliseconds. So we're not a high-frequency trading application, for instance. So that's for the 5 to 15 seconds, sort of general bounds that we want to have. And it's, I should add that it's roughly the same order of magnitude of an SMS, which is really the highest medium, the medium with the highest urgency that we typically deal with. The second consequence that the real-time application drove into, or the constraint that it gave us, is that one of concurrency. So by concurrency, I mean that when you have to deal with data coming from different sources, they kind of have to show up, roughly in sync. So it doesn't really work if you have, you're getting metrics from only half of your clusters now, and then the other half, in 2 minutes. Or you're getting all your metrics, but you're missing your alerts, and so on. So it's really important that we try to present concurrent data roughly at the same, concurrent data derived to us should be presented to the user as concurrent. Now, the interesting consequence for us is if you're sort of watching real-time data come in is we have no real idea of what it is that is interesting. So what that means is in terms of access pattern, what data should we keep hot and fresh and ready to present is at this point is pretty much everything that's happened maybe in the last 1 hour, 2 hours, 24 hours. So we need to keep all the data that arrived for a specific window of time, because if you're looking at a news feed or if you're looking at some real-time graph being updated, you might look at one particular dashboard now, another dashboard later. There's no real way for us to predict what's interesting and what's going to happen, obviously. So that's going to have a particularly interesting consequence of the way we put the architecture together. I would say the last consequence of the real-time aspect is, and that's really, I think, the canonical argument for DIRT, is high tolerance to noise. So by that, I mean we're not a system of records. So we've built an application where we get signals from all your infrastructure, but we're not ultimately the place where you want to go to see everything in detail, down to the last, micro detail. The application we built is really much more to make real-time decisions based on looking at signals that come from all over the place. And if you want to drill down, if you say, there was a release that happened 5 minutes ago, and you want to see exactly the content of the release, we'll give you a pointer to that, to go back to the system that originated that signal, hey, there was a release that happened 5 minutes ago. But this is not, we're not the place where we're going to store that data. So, because we really want we want to help you make real-time decision. Basically, we in accordance to the DIRT principles, will rather drop individual data points rather than be late. And that applies to continuous metrics. So, for instance, to talk about your number of concurrent sessions right now, or number of so say sessions a system, it's much better, obviously, to be on time, and you have, so at time t, you have your number. At time t plus 1, where you were supposed to take a measure, you're missing that measure. At time t plus 2, you get a new measure. It's OK for us. In other words, and that's maybe to make it a little bit more concrete, imagine you're crossing an urban, sort of busy urban intersection. We'd much rather be in the case where you're going to cross, you have real-time data, you're going to cross the intersection, but like me, you don't have your glasses. So I see you like kind of blurry, but I get a sense in real time of what's happening. As opposed to perfect vision being, I'm going to cross this intersection, but I see everything except it's through a video feed that's 5 minutes late. So obviously, if you worry about your safety, you want to take your chances and survive noise, but really no latency, please. Now, in terms of, so I've talked about the real-time consequences of our applications onto what it is we're doing. In terms of the data intensiveness, it's slightly different. So the first thing is that it's one of storage. So now, when you want to look at data, when you want to explore patterns, sort of ex post after the fact, you have all your signals. I want to see what happened. We had the same problem like a week ago. I want to see what happened. What kind of alerts we got, what were these metrics, at what levels were there, and so on. It's a completely different scenario, which we also want to support. So that scenario is ultimately driven by business cycle. The amount of storage that we need is ultimately driven by business cycles. By that I mean, so let's say you are in, I picked 2 examples, retail or education. The kind of data you care about is data over the past year, pretty much. For retail, it's fairly obvious. You want to see sort of Christmas to Christmas, Thanksgiving to Thanksgiving. For education, it's also the same. You want to see, how you're, and that's the industry I was in before. You want to see, how a particular cohort of students is doing in terms of tests versus what they were doing at the last year. So what that means is we need to keep data for, in this case, for a little bit over 12 months. And if you remember correctly, I said, we're building this new app, this new real-time app that lets you sort of explore data, and we had on a limited budget. So for us, it was really important to have elastic storage, so not something where we'd have to spend a lot of money upfront to buy expensive storage. So that being said, even though now we're not so much in the real-time aspect of the application, but the data-intensive part of the application, latency is still important. And it's important it's important mostly because we're used by people. And when you're looking for patterns, you're going to explore your data set, and see, let's see, a month ago what happened. Did we have, what kind of alerts again, what kind of releases do we have, what was the velocity in terms of development speed and so on. So you're looking for patterns, you're forming in your head a sort of mental model. You still want to have a round trip when you're asking questions of the data that's about 300 milliseconds, and that's kind of the target we have. The main reason there, and that's not tied to the kind of data we're looking at, is really kind of universal to like using computer systems, is that if you go beyond that 300 millisecond, then it gets, you lose a lot of productivity because you basically end up waiting on the system. So the problem with that, though, is that, so for the real-time feed, we knew that we want to present real-time data constantly, so we kind of have to keep all data for the last, say, hour or 2 and so on, so you can quickly show on the screen what happened the last 2 hours. For long-term data, though, it's kind of a different story, because it's much harder for us to predict what the access patterns are. So if you want to look at your number of, I don't know, closed or half-closed TCP connections, the maximum for this particular cluster over the last year, then it's, that's one thing because it's interesting to you. But that might not be interesting to somebody else who works in an organization who, is interested in another kind of data. or somebody who's working in a different organization. So what that means is from an access pattern perspective, we have this ginormous amount of data, and it's really hard for us to predict where you're going to go next, because that's really run based on what it is that you find in the data and the questions you're asking of the data. So, typically we'll make two kinds of trade-off there, because it's a lot of data, but we still want to present it in under 300 milliseconds. We'll pre-compute as much as we can for things that we know are going to be of interest, typical like distributions, like simple statistical moments, and so on. And then we'll do another kind of trade-off, which is that especially true for time series, when you're asking for a longer period of time, I want data for an entire year, for instance, we'll give you, and that's a classic trade-off, we'll give you basically lower resolution data. So we'll give you could be the maximum, depending on what you ask, we'll give you the maximum load over a cluster over the last year, for instance. But we won't give you, even though we sampled every 15 seconds, we'll give you data we'll aggregate data up to the hour, up to the day, and then we'll deliver that data to you. I should say that, for people who are familiar with like RRD, it's different. So RRD is really, it samples the data, and then you roll up data, and then you lose the resolution in our case, and we'll see how that impacts the architecture. We're not losing resolution. So the typical way you do it is, so if you give me data for a year, well, we'll give you 500 points of a time series, so 500 samples for an entire year. If you want more details, well, all you got to do is zoom in, basically. And that's how it's different from RD. So, a representation of Datadog in the middle, getting constant telemetry from your servers, your apps, and so on. That sort of forks into the real-time people who are more interested in real-time data, and then people who are exploring data. And so here, we get the data that aggregates. You people who want to watch and share, have sort of a real-time updates, so news feeds and so on. Graphs that change in real time. And then you have people, different use cases, who are looking for patterns. So they want to do some kind of visualization or do some background data analysis looking for patterns in the data. So here I've mapped sort of the acid, base, and dirt. I've mapped I've mapped them to these use cases, if you will. So on the aggregation side, is two things. First of all, so we get a ton of data, which we have to save as it arrives. We have to make it durable. We also have to make it sort of readily available, regardless of how much data we have saved so far, to serve the use case on the top right. So that's the data-intensive real-time aspect of it. And for people who are who are looking for patterns, the kind of data store they're interested in is much more like a base data store. So something where they'll be able to request kind of, regardless of how much data it is that you're looking at, they should always be able to request it and get the answer. Okay, so we're almost at the point where I can actually show you little boxes and how it fits together. So basically, Datadog is a mix of acid, a little bit of acid, dirt, and base. So how it all fits together, the mullet at long last. So that's it in more detail. And maybe I want to spend a little more time. So it's all SQL in front, no SQL part in the back. That's not how we started, actually, but so if you remember, let me just go back to this guy. Okay, so the mullet is the dog in the middle. Oh, is it moving? Oh, yeah. Sorry. Okay, so you have you see the API little thing. So the API thing is basically what we call the intake, and I hope it's legible. And that's really the signals that arrive from all over the universe that's around you. So you have what we call telemetry data, so raw data. So it's your metrics, from all your systems, your apps, your alerts, your Your source code commits even, we'll ingest that. So we'll take as much as possible. And once it arrives in the intake, the role of the intake is fairly simple. Is basically to make sure we have the data. So it is first to so the first thing it's going to do is going to take the data and put it in a in-memory data store. The reason why we have to do that is to serve the real-time use case. So because when you're watching stuff in real time, when you're watching sort of what's happening, you have a dashboard and you have your little graphs that are evolving. It doesn't make a lot of sense to take the data, write them to disk, and then read them to disk again, because we know we have to serve it. So what we'd rather do is just stick it in memory. We know it's going to get consumed, and it's going to stay in memory for like 2 hours, 4 hours, a whole day, depending on how you want to set it up. But it's super fast access, and it serves the real-time use case very well. The second thing that the intake is going to do is it's actually going to dump the raw data into a durable store. And that durable store, the reason we want to do it is basically if the rest of Datadog goes to crap, then we have the data, we restart everything, and we'll be able to resume processing. So the key thing, though, is that the amount of data received is sort of keeps increasing. So that data store has to be durable, and it also has to be elastic. So elastic in the sense of from a cost perspective. So it's something where we know we can put more data, and our cost function is going to stay, so let's say, roughly linear. So now the intake's taken and the third thing I should say that the intake's going to do is going to just take the exact same data, parse it a little bit, and queue it for processing. For processing that is not necessarily required to get, to present our real-time feeds, but processing where we're going to pre-compute some statistical moment and so on. So the intake is sort of split the data kind of 3 ways. The same data go through a system of queues, which will then be processed at some point, which could be a second later, it could be 15 minutes later, depending on how the queues, how big the queues are, how many processors are online, and so on. And the processors, what they do is they'll do the computation, they'll stick the results in the durable store, and they'll also put some interesting metadata in a SQL data store that's there. So now, basically, we've done the path from the rest of the world into Datadog. Now the question is, and that ends up in that data layer, that mullet thing. Now the question is, how do we get data out? So data out, again, is heavily driven by the kind of use case, how you're using Datadog. If you're using Datadog to get real-time stuff, or if you're using Datadog to explore data. If you're getting real-time stuff, then we're essentially streaming data, and straight from the data mullet or data layer. And streaming data really means hitting the in-memory data store for the most part, hitting a little bit the SQL data store, for things like, well, what data do you have access to for ACLs, but that's about it. If on the other hand, so that's if you're the little guy sort of on top of the computer, watching stuff. If you're looking for patterns, that's the guy at the bottom. You're also hitting the same data mullet, but of course inside the requests are going to be routed differently, because you're going to sort of in a very bursty fashion, you're going to ask, okay, give me the aggregate of this metric over the following groups of sources. And then you're going to get the data back, and then you're going to think about it and say, okay, try to make sense of the data. And that's going to bring you to your next question, where you want to understand, all right, now I have this data. Show me another kind of data which I think is connected, and I think there's some kind of correlation. In terms of actual stack, and that's where I'm going to drill down further. So we picked 3, one for each class of data store. We picked Redis for in-memory. We picked Cassandra for sort of durable, elastic. And we picked Postgres for SQL. And I want to pretty much spend the rest of the talk explaining how we made these choices. So we considered five axes to choose. The first one is the volume of data that the data store is sort of comfortable storing and serving, with decent latency, with latency that are compatible with the numbers I cited earlier. The second one, is general latency. If we read some data, how fast can we expect some response? So of course, there's going to be, depends on how much data you're asking, et cetera, and how complex the query is. But in general, order of magnitude, what is the latency? The third aspect is really down to earth. Is does it wake me in the middle of the night? And that's particularly important for, if you're a young company, you have staff is, have a small team, you kind of want something that's going to work. Fourth criteria is the community, because that's more, from a development standpoint, how easy is it to code against. And the last axis that we considered is one of cost. So like what is driving our cost in that particular, for that particular data store? So starting with sort of durable elastic storage, we considered in this order pretty much five different stores. There are zillions of more. Why we picked those is a mix of what we know, what we've heard of, what people say. It's really down to that. We didn't do an extensive survey of all no-SQL storage that exists, or SQL or no-SQL storage that exists. But these are the things that everybody's heard of, maybe with the exception of the last one. So the first thing we looked at Postgres for the kind of problem we have where you represent time series. The thing though is, you could do it very naively where you say, for a time series, so a timestamp and a value, I'm going to go and represent one row per data point. So it has a number of problems, one of which is you arrive at billions or hundreds of billions of rows really quickly, so it's not even worth going there because you have a lot of data points coming in. And the second thing is the realization that the itemized data point for a time series has no real, has very little value. It's really, it has more value when you look at the data points for the same time series around it. So if you want to see, so you can have one value that's not very useful. It's much more useful when you have time series, say, for an hour, because then you can compute averages, distributions, percentiles, and so on. So if you're not storing time series as individual data points, so one row per point, per series, per timestamp, then you end up doing something that that works, which is to store your time series as a blob in the database. So you can consider each time series, the equivalent of each graph is going to end up as a blob, as a record in the database. The problem, though, with that is that blob management is just not that much fun in Postgres, or I should say in Oracle is the exact same thing. It's just not. So that's why we said, what, it's let's not go there. It's doable. We've done it, but that's not where where we'd want to go. So the second one we considered is Mongo. Mongo, I would say, from a personal experience, mostly because it has excellent developer marketing. So they're everywhere. It's and the only thing for us is in early 2010, the durability was sort of in question. I wouldn't say that we deep dived to exactly make sure that is it actually durable or not durable and so on. But there were enough signals from the rest of the community saying, oh, I tried, it doesn't work, and I tried too, it doesn't work, and we had this problem, that we said, let's just not go there. We don't have the time to deal with that. We looked at SciDB, which is a Stonebreaker, like scientific database, which on paper is really what we want. It allows you to represent, essentially time series, do complex matrix operations on them. It's built to store stuff like, from the HLC, or when you have a ton of scientific data, like terabytes and terabytes every hour. The problem for us, is that it was just too early, and it's still, I think, very early. So I think it works in the context of a scientific project when you have maybe the time to explore, and besides, that's the only tool that's going to work. But for us, we passed basically, which left our pick, Cassandra, and I'll talk about Riak very briefly. So Cassandra, quickly, basically. Facebook said, well, it runs on a couple of hundreds of hosts. We have 150 terabytes of data in 2010. Said, okay, that's fine. That's the kind of scale where they're already there, so we can get there. It's very easy to distribute data around a growing number of nodes. It has durable quorum writes, so which is important when you're looking to have durable data. In terms of latency, on writes, it's pretty good. On reads, it's a lot more variable, and I want to talk, especially in EC2, and actually specifically on EC2, and I want to talk about that in a bit. From an ops perspective, we found that it was just, if you had asked me, middle of this year, I would have said Cassandra for me is like 4 words. It's blood, toil, sweat, and tears. And the reason for that is, I think, inherently is because the release engineering was too aggressive. And I can understand the reason and so on. But we went through 10 releases. That was for the stable branch. We went through 10 releases from the beginning of the year. And it's only at the end, like in the past, I would say 3-4 months, that things got to be more stable. And from an ops perspective also, it has some annoying idiosyncrasies, like the config file that's used once but never, only the data you put in is used once and then it's never used again, which is kind of strange. The disk queues is also hard to predict. I mean, there are a couple of bugs open for, when it uses more and more disk and never reclaims it properly. From a dev perspective, I think the most striking thing that we got back was that the nomenclature is really bizarre. You have rows, you have columns, then you have families. I mean, I don't know where the family come from because there are no parents, no children, and nothing. So I don't know why they wanted to avoid table because look, it has rows, it has columns. Yes, it's not a square or rectangular table, but like you can call it a table, and everybody will be happier. The data access is a little bit cumbersome. It forces you to clearly think your data model based on what kind of access you have in mind. So you have to know how you're going to access the data in the first place. The semantics in terms of query are like light years behind SQL, and I know that now there's CQL that sort of makes it a little bit more easy to write queries against, but the kind of stuff you can do with SQL, you just can't do that. Luckily, it has good libraries, so we're okay. At least we can code to it. In terms of costs, I think where we suffer the most is in ops time, and that's really like sleepless nights trying to get things working. The cost is also something that is ultimately driven by the amount of I/O that we're doing, and so. What we found is that we couldn't go beyond a certain threshold in terms of I/O reading and writing. So the only thing we could do then is basically add more nodes, distribute the data more thinly. The problem when you do that is just the cost of adding extra nodes just adds up. One thing I want to say about Riak, we actually prototyped the system on Riak after like 2 or 3 versions of Cassandra, or out of spite of Cassandra, basically. We're like, F it doesn't work, let's switch. We happen to love Erlang, the Basho people are great. The only thing for us is that, we're at the point where we're going to do the switch, and at the end it's like, okay, let's do one last release of Cassandra and one upgrade. And that was the one that kind of made the worst problems go away. So we ended up never merging. To this date, our Riak use never left prototype. But I think if we were to start again, we might start from there. Okay, so that was for the the in-memory, the durable elastic storage. For in-memory, it was a lot simpler. We're starting with Redis, and then we just stopped looking because it was so great. It scales to the amount of RAM that you have. It's very easy for us to partition the data based on accounts. The latency is awesome. Less than 5 milliseconds, easy. It's dominated by network usually. From an ops perspective, there's nothing to do, so I kind of like that. It's just boring. That's how I love it. From a dev perspective, it's also it's brilliant. The docs are clear, simple protocol. All the data structures you need are there, so it's awesome. And the cost is directly driven by the amount of RAM we need, so that's easy to predict. There was somebody made an unsavory but I think powerful analogy of sort of Redis is the AK-47 of databases, which, well, for what it is. But I think it works. Not that I've ever used an AK, but. Now, in terms of SQL, so we love SQL as a language, so we really wanted to try to keep it. And we had been exposed in my history, in my career, I had been exposed mostly to Oracle and Postgres. So starting with Oracle, it's kind of easy because to run Oracle with all these options on this laptop, I think it would cost me $256,000, something like that. And that's so. 138 for 2 cores, and you add 22% license, annual support, and you pay for license. So Oracle is really this for us. Just too much. So that left Postgres. So in terms of volume data, we knew we could get it to the high number of gigabytes, low number of terabytes at least, without going crazy. Latency after you run explain, analyze, you can get it down to it's like 10 milliseconds and so on EC2. For an ops perspective, it's almost as boring as Redis, not quite, but almost. It's very well understood by a certain class of engineers, of software developers. So people who actually don't have a prejudice against SQL are able to do beautiful things with it. And the cost is, I would say, mostly a function of how much latency we want in storage. So, that, which is a little bit vague, I agree, but that's that. A couple of things we didn't look at, but we wanted to. VaultDB, I know there's a talk right now about Vault. I'm super interested in it. Could be an interesting match for real-time stuff if we need to move out of the Redis. The only thing is that it's all stored procedures, so I don't really like to code in stored procedures. We also want to keep an eye on homegrown data stores, things like Rainbird. So that's sort of out of Twitter. I mean, anything. If you know of any sort of efficient time series data store that's open source, we're definitely willing to look at it. So in short, the data mullet we got it to run. It's all open source. It's if you're ready to dive in code, so you can make it work. It's great because there's zero capex, so it's all OpEx and EC2. The problem with running data mullet in EC2 is we hit I think what's a structural weakness of that particular public cloud, which is basically shared network I/O. So latency at moderate throughput was really bad. So we got to see stuff like you'd have a huge spike out of nowhere and oh shit, what's happening? And it turned out to be we're just asking data in the wrong way. And it was really easy for us to really clog the pipes. So here I've represented the average weight for the device that contained in this case, the Cassandra volumes, the average weight versus the service time. So it would take, and these are maximum numbers. So it would take 5 milliseconds to serve for the device, for the network device, the network storage device to serve the data. But it would take 670 milliseconds for the machine to get the response back. It was just too much stuff being pushed through. And we're not talking about an insane amount of data. We're writing 100 megs, reading 30 megs. So it's not like out of this world. But that's what we got. Another example in this case is kind of same data, slightly different representation. And that's focusing a number of transfer per seconds. So you can see the service time, 1.3 milliseconds is great. The average wait, though, it's in the hundreds of milliseconds. So we're trying to push and pull too much data, so things just pile up because the underlying devices cannot serve data fast enough. How do we mitigate that? So I already alluded to it. On the Cassandra side, what we basically our way out is just more nodes, more RAM, more partitions, more parallelism, just more money, just basically grow in number of nodes. So that's doable for a while. But this obviously is going to be more and more money spent there. For Postgres, the I/O mitigation strategy is different. I think we can scale up to a point, and that's been definitely in Oracle world. That's how you do it. For Postgres, I think it makes also sense to scale up, so you just get a bigger machine because it's very cheap, basically. In terms of complexity, you're not trying to do replication and so on. But at some point, we'll do you have to do replication. One thing that we're looking at, though, is maybe move some parts to bare metal just to get better sort of I/O banks for our bucks. So in all, it's a well-trodden but difficult path. That's it's been done before, but it's never become like super easy. What we could do instead, and what we're looking at is to actually have lower our dependency on long-term storage, or I should say rather, lower our dependency on answering questions using data that's not readily available in RAM. So things we're looking at is adding more and more stuff in RAM as much as possible, and also archive. So keep the if you will, outsource the durable storage to Amazon completely by, for instance, using S3 and CloudFront to store data. Because when you think about it, the data we receive and manage is inherently very time sensitive and very time specific. Stuff that happened last year, it's not gonna change in 2 years. So it's really immutable, and it's in our obviously we can easily just move that out. I think if the equivalent would be if you think about, if your geographical equivalent, you think about like Google Maps, where you'd serve tiles of maps out of the cloud. So that's something we want to do. But instead of having tiles of maps, we want to do of geographical maps. We want to do tiles of time series data. Last digression before the end. The EC2 acts as our very own chaos monkey. These are 2 bugs that we've been hit with, and that's kind of interesting. So every so often, and that's something that I think it's much more prevalent on public clouds than if you run your infrastructure, because we never had that many problems on our own bare metal. Is that you'll have like machines disappear, and sometimes machines disappear for a bad reason. And in the second case, I think the high load, you'll get stuck with that problem happening depending on what processor your machine is running on and what version of the kernel. And either you recompile your kernel or you try to spawn a new machine that has a different processor, but that leads to distractions that are really unwelcome. So, as a takeaway of this, I would say that, so basically we've built the mullet with just open source stuff. We haven't spent a dime on licensing. It was relatively quick, I think, given the size of the team, and we didn't have to spend a single dime on infrastructure. So, I think that was good. We learned some interesting things along the way, and I'm happy to answer any more questions at this point. Yeah. So the question is, what do we use for queuing? We actually settle on something that's relatively new called Kafka from LinkedIn. That does fairly simple disk-based queuing. So I would say, from an architectural, it uses the VM, the property of the OS, the VM, and the efficient storage and serving of files to be able to have a very simple queuing system. You have semantics that are simpler than MQs. It's easier to deploy. and it still gives you durability. So that's what we've been using. Oh, yeah, so first here, sorry. Yeah, the question, did we look at OpenTSDB? We looked at the, very interested, the only thing is, I think with OpenTSDB, which is a time series database, it sounds like it's the best thing for us. It's based on HBase, which then requires HDFS, name nodes, and so on, the whole Hadoop stack. And it was, when we were just beginning, it was like, I don't want to spend the next, 3 weeks setting up the stack. So let's get that. That's how. That's my answer to that. Yeah. 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 Right. That's when we were. So that's what we observed when we were asking for data through Cassandra, in a way that was similarly innocuous. So it wasn't clear that we were asking things. It's not like we were doing cardinal. How do you say? Doing like missing a joint, if you will, the equivalent. It was just surprising that it hit us so hard. And then because of this distributed nature of the queries, it hit us pretty much everywhere, at least on all the replicas of the partition. So practically speaking, what you see, and that's, I think, what mattered, is that so everything is kind of fine, and then all of a sudden, everything goes to shit and you're like, what happened? It's not like we're firing more and more requests, and then you hit the threshold. It's just you're running the bad one. And I think in the SQL world, you would say, well, look at your plan and see how things are going. Oh yeah, this is dumb. You forgot this. Or I think in the no-SQL world, there's no such thing, and that's what we saw. And I think the network storage basically is a lot less forgiving than if you've invested a lot of money in a nice SAN, which is dedicated to you, and this is fast drive and so on, or SSDs, then it's a lot more forgiving. Yeah. The question is, are we using EBS? We're using partly EBS and then partly instance volumes. Yeah. So EBS, we use it for, so for instance, since we use Postgres, we use EBS for Postgres because there's no, even though we do replication of our Postgres instance, just if we lose one volume and we have to fail over, it's just much more of a pain than relying on EBS. Yeah, go ahead. So, including APIs, 3 people, 3-4 months, I would say. Yeah, and that includes and that includes basically trying to figure out what it is. As a startup, you start and you're like, okay, we think we have this idea and this is the direction we want to take, and then you have an idea of the product. But in reality, I think you're trying to figure out what you're trying to figure out as you build. So I think if we had known exactly this is exactly where we want to be, this is exactly how you can probably do it faster. But it's not a 20 people for 2 years effort. All right. Well, thank you very much.